Welcome back to The Explainer. Today, we're unpacking a really fantastic breakdown from the 150 Cloud Architecture series.
Right, and if you're just starting to learn Kubernetes, you're probably completely obsessed with pods, deployments, and services, because, well, that's where your code actually lives. But today, we're looking behind the curtain at the true brain of the operation, the control plane. Let's dive right in.
Picture this. It's 3 a.m., your core application goes down, and suddenly you're dealing with an agonizing pager alert. You're logging into servers, manually restarting services, just totally bleary-eyed. We've all been there.
Oh, absolutely. But here's the thing. With a properly configured Kubernetes cluster, you literally just sleep through it. Why? Because the control plane is rescuing you while you sleep. It forces this complete shift in how we think about infrastructure. We aren't just running containers on virtual machines anymore. We're orchestrating desired states. You tell the system what you want, and it does all the heavy lifting.
A really great way to visualize this is to treat your cluster like a bustling city. So you've got your worker nodes, right? Those are essentially the physical buildings of our city. And the pods running inside them, those are the people living and working in those buildings. But a city completely descends into chaos without some form of governance. And that's exactly what the control plane is. It acts as the city administration. It's constantly answering these critical questions. Is a building at capacity? Are the residents healthy? Do we need to zone a totally new building? Without this management layer, Kubernetes is really just a collection of unmanaged VMs.
So here is our architectural blueprint for today. We'll cover 1. The brain of the cluster. 2. Anatomy of the control plane. 3. The magic of self-healing. 4. Managed services and cloud integration. And finally, 5. Best practices for architects.
All right, let's get into part 1. The brain of the cluster. So why exactly are we looking past the workloads themselves? Well, it's because the control plane is the underlying engine making every single scheduling decision and self-healing event possible. And it's basically made up of 5 core components: the Kubernetes API server, etcd, the scheduler, the controller manager, and the cloud controller manager.
Exactly. It is definitely not one giant monolithic program. Working together, these 5 components form a really unified management layer. They're constantly monitoring the cluster, ingesting data, and making these split-second decisions to keep your apps highly available.
Moving right along to part 2, anatomy of the control plane. First up, the Kubernetes API server. Think of this as the absolute front door to your cluster. Every single request has to pass through this critical entry point. Whether it's a developer running kube control, a CI/CD pipeline, or even internal components, they all talk to the API server.
Right, and acting as that bouncer at the front door, it handles authentication to verify who you actually are, authorization to check if you even have permissions, and validation to ensure your request isn't malformed. It is the ultimate central communication hub.
And right behind that front door sits etcd. If the API server is the door, etcd is the vault. It's a highly available distributed key-value database, acting as the definitive system of record for your cluster's desired and current state. I really cannot stress this enough. If you lose your etcd data, you lose your entire cluster. Period. I actually once saw a team accidentally delete their etcd cluster without a backup in production. And let me tell you, it was an absolute resume-generating event. Rigorous backups and strict encryption are completely non-negotiable here.
Next in line is the scheduler. So when a new pod needs to be created, this component acts kind of like a highly analytical matchmaker. It decides exactly where that pod should run, and it definitely doesn't just guess.
Not at all. It evaluates available CPU and memory, it checks node labels, looks for taints and tolerations, and calculates some pretty complex affinity and anti-affinity rules. Only after crunching all of those constraints does it assign the workload to the absolute best possible worker node.
Then we have the controller manager. This is the piece that runs the famous reconciliation loop. Imagine you deployed a web app and you ask for 3 pods, but suddenly a node crashes, taking one of those pods down with it.
The controller manager instantly spots that discrepancy. It obsessively compares your desired state, which is 3, against the current state, which is now 2. And without a single bit of human intervention, it kicks off the process to spin up a replacement and get you right back to 3.
Architect A, and the final piece of the puzzle is the Cloud Controller Manager. This is the bridge that lets your cluster talk directly to the underlying infrastructure of your specific cloud provider.
Right, so if you ask Kubernetes for a load balancer, the Cloud Controller Manager actually reaches out to AWS to provision a native application load balancer. Or if you need a persistent disk, it hits up Azure or Google Cloud to mount that native storage seamlessly. It's pretty amazing.
Which brings us to Section 3, the magic of self-healing.
Let's trace just how incredibly fast this happens when things go sideways. Step 1. You submit a manifest to the API server asking for 3 replicas. Step 2. That desired state is securely stored right into etcd.
Then step 3, the scheduler selects the best healthy worker nodes. Step 4, the pods are actually created on those nodes.
Exactly. And step 5, the controller manager continuously monitors the whole situation. The very second a pod dies, the controller tells the API server to make a new one. The scheduler finds a fresh node, and boom, recovery happens instantly. Manual intervention is completely out of the picture.
All right, Section 4, Managed Services and Cloud Integration.
Now, building and maintaining this control plane yourself is incredibly complex. But if you use a managed service, the dynamic shifts entirely. In a managed environment, you are only responsible for your worker nodes, your applications, namespaces, and access controls.
And the relief here is just massive. The cloud provider, whether we're talking Google Kubernetes Engine, Azure Kubernetes Service, or Amazon EKS, they completely manage the API server, etcd, the scheduler, and the controller manager. They handle the high availability, security patching, the upgrades, letting your team actually focus on building software instead of managing servers.
And finally, Section 5, Best Practices for Architects.
Let's do a quick rundown of the pitfalls that lead to operational nightmares. First up, assuming Kubernetes is just containers rather than treating it like the complex distributed system it is. Second, ignoring control plane availability. If the brain goes down, you can't update or fix a thing. Third, neglecting those etcd backups and self-managed clusters. Fourth, completely overlooking scheduling policies, which usually causes workloads to clash on the wrong hardware. And finally, fundamentally misunderstanding the concept of desired state. That's what leads engineers to manually try and fix things that the system is literally already trying to resolve itself. So to counter those, here are our hard-won best practices. Use managed services like GKE, AKS, or EKS whenever possible. It's almost always the right call. And lock down that front door. Strictly secure API server access using least privilege RBAC.
Yeah, and if you absolutely have to self-manage, encrypt and obsessively backup etcd. Also, monitor your control plane's health and latency metrics. Sluggish API responses almost always mean a sick cluster. Finally, intimately understand your scheduling constraints to ensure your critical workloads land exactly where they belong.
Architect A, I really want to highlight a quote from our source material today. Rather than manually operating infrastructure, we define the desired outcome, and Kubernetes continuously works to achieve it. That really just captures the true philosophical leap required for modern cloud-native architecture. You aren't giving Kubernetes a rigid checklist of tasks. You are giving it a blueprint of the end goal. And this declarative model is exactly what transforms a static collection of servers into a dynamic, highly resilient platform. Architect A, understanding the control plane is really what separates a novice from an expert cloud architect. It's the decision-making engine that ensures your applications remain healthy and scalable. So take a hard look at your own deployments today. Is your cluster truly self-healing, or are you and your team still stuck manually operating infrastructure when things go wrong in the middle of the night? Something to think about. Keep building smarter, and we'll catch you in the next explainer.